Okay, so our first example is the adiabatic nozzle. All right, and so you remember the adiabatic nozzle, or a nozzle in general, takes the purpose of it is to increase the velocity of the fluid. Um, okay, so we got to dissect this a little bit. Let's understand what the problem is saying. So the substance is steam. All right, so we have water. P1 equals 3 MPa, 3 megapascals, which is 3,000 kilopascals, which is 3 times 10 to the 6 pascals. All right. Okay. The temperature at the entrance is 400 degrees C. All right. It's adiabatic, meaning Q dot in equals Q dot out equals 0. All right. It's steady. So and so the mass balance simplifies to that, and the energy balance likewise does the same. So E dot in minus E dot out equals 0. So M dot in equals M dot out, and E dot in equals E dot out. All right. So steady V1 V1, the velocity one, the steam enters the nozzle at 40 meters per second, and it exits the nozzle with a pressure of 2.5 megapascals, and at 40 meters per second. No, 300 meters per second, I'm sorry. Okay, so all right. So let's write down the energy balance equation. So it simplifies, remember, to E dot in equals E dot out. So E dot in is M dot in theta 1 plus any work interaction in plus any heat interaction in, and E dot out is basically the same quantities but on the exit. And we know that it is adiabatic. We know from the fact that it's a nozzle and that there is no work interaction. No work is exiting the system, right? So if I make the boundary here, there's no work exiting the nozzle. So these go to 0. So the situation becomes the energy balance basically simplifies to M dot in theta 1 equals M dot out theta 2. And because it's a steady situation, I have the M dot in minus M dot out equals 0, or these are similar. these cancel, and so I just get this simple relation, theta 1 equals theta 2. All right, so now let's expand that. So theta 1 is the enthalpy at 1 plus 1/2 V1 squared plus GZ1 equals H2 plus 1/2 V2 squared plus GZ2. All right, so now let's rearrange this a little bit. So H1 minus H2 equals 1/2 V2 squared minus V1 squared. Okay, and then plus G Z2 minus Z1. But this is going to come to 0. All right, so this is basically our sort of new energy balance for this particular equation, or for this particular device. And so we have a sort of a measure of the thermal energy content of the system being compared to some change in the exit, or I'm sorry, the thermal energy content of the fluids at the entrance and exit equal to the kinetic energy, equal to a change in the kinetic energy at the exit, or the entrance versus the exit. Okay, and so we're exchanging enthalpy for kinetic energy. That's what we're doing. Okay, so what do we know? We know enough. We need to find H1, and we have two intrinsic properties. We got the pressure and the temperature. They because we're given pressure and temperature as the only sort of intrinsic properties of this fluid, we have to, we hope that these two are independent, and in fact they are in this particular case. Okay, so if they weren't, I'd have to give you another piece of information to distinguish the actual state, but they are independent in this particular case. They are superheated fluid in this particular case. So so the H1 is just going to be the enthalpy as a function of pressure at 3000 kPa and at temperature of 400 degrees C. And I go into my calculator and I can figure that out. That's 3231.7. Now, H2. The purpose of the question is to find what T2 is. Okay, so I know V1, V2, the only unknown in my energy balance is H2 itself. So I can rearrange for H2. H2 is equal to H1 minus so that's H2. And the sort of the strategy here is I can take T2 to be equal to a function, the temperature as a function of the intrinsic property I have, which is pressure that I'm given. And I need another intrinsic property, but I can get it from H2 because I know every value here. So I can get whatever H2 is. Okay. So doing the calculation, I get V2 squared, which is 300, minus V1 squared, which was 40, right? Yeah, 40. Okay. Now we have to be really careful because the units here are meters squared per second squared. Okay, and that is, if you remember from back on our units discussion, this is joules per kilogram. These are joules per kilogram, not kilojoules per kilogram. So you have to be very careful about your units here. So our enthalpy is in kilojoules per kilogram, but the calculation we just did for the change in kinetic energy gave us joules per kilogram. All right. And so we have to multiply this. This is off by a factor of 1,000. All right. So H2 is 3231.7 kilojoules per kilogram minus 44.2 kilojoules per kilogram. Okay. All right, so now I have enthalpy at the exit, which would allow me to calculate the temperature at the exit because I have the pressure and now I have an independent intrinsic property. And I run that into my thermodynamic property calculator. Okay, so there's part A. The part B. Just from the, so for part B, we take into account the mass balance, right? So the m dot in equals m dot out. Now we have to make the further assumption that it's incompressible fluid. Which means the density is constant. Actually, that's not true. So m dot n is rho 1 v1 a1, and m dot out, or m dot 2, I guess, is going to be rho 2 v2 a2. And the question involves finding a1 over a2, so I can just simplify for that. So a1 over a2 is equal to rho 2 v2 over rho 1 v1, which is the same as specific volume 1 v2 over specific volume to V1. Okay, and so I have all the properties I need. So V1 is equal to the specific volume as a function of pressure, and that equals and likewise V2 is a function of the pressure at the exit, and we could use temperature if we wanted to. You know, we have that value now, but just for consistency, I use so I run this into my calculator, I get this value, and so now I have everything I need. So A1 over A2 is equal to and I need the velocity at state 2 is 300. Velocity at state 1, or at the entrance, is 40. And this is going to be unitless, right? The units cancel here. I got the same units on top as I have on the bottom, and so they cancel, and I have a unitless ratio.